heat capacity and specific heat capacity of substances. The heat capacity of a substance is the quantity of heat energy required to change the temperature of that substance by 1 degree Celsius or 1 Kelvin. Heat capacity in terms of formula is equal to quantity of heat energy supplied divided by the change in temperature. We use capital letter C to represent heat capacity is equal to Q, that's the quantity of heat energy, divided by the change in temperature, which is final temperature T2 minus initial temperature T1. The unit of heat capacity is joule per Kelvin or joule per degree Celsius. Specific heat capacity of a substance is the quantity of heat energy required to change the temperature of a unit mass of the substance by 1 Kelvin. Specific heat capacity represented by small letter c is equal to the quantity of heat supplied divided by the mass of the substance times the change in temperature. Specific heat capacity equal to Q for quantity of heat energy M, mass of the substance, then change in temperature, theta 2 minus theta 1. Specific heat capacity is Q divided by M theta. The unit of specific heat capacity is joule per kilogram per Kelvin. Now if we cross multiply, we get quantity of heat energy gained or lost by a body is equal to mc theta, where m is the mass of the body, c is the specific heat capacity, theta is the change in temperature. Specific heat capacity is equal to the heat capacity per unit mass of the substance. By this I mean specific heat capacity is equal to heat capacity of the substance divided by the mass of the substance. Specific heat capacity of substances can be determined by 1. Electrical method, 2. Method of mixtures or contact method. Electrically, that's electrical method. We make use of the fact that the electrical energy supplied is equal to the heat energy gained by the substance. To determine the amount of electrical energy supplied, any of these formula could be used. Power times time, energy is current times voltage times time, or energy is current squared times resistance times time, or energy, that's electrical energy, is voltage squared divided by resistance times time. Then of course the heat gained by the substance is mc theta. Then by electrical method, we make use of the fact that when two bodies are in contact, one will gain heat and the other one will lose. The heat energy lost by a body called P must be equal to the heat energy gained by another body that is in contact called Q. Whether the body loses heat or gains heat, we make use of mc theta for determination of amount of heat energy gained or lost. Here we have mc theta for P, which loses heat, and here we have mc theta for Q, which also gains heat. M here represents the mass of P, specific heat capacity of P, change in temperature of P. Whereas for heat gain, M here represents the mass of Q, specific heat capacity of body Q, and change in temperature of body Q. Example 1. An electric current of 3 amperes flowing through an electric heating element of resistance 20 ohms embedded in 1000 grams of an oil raises the temperature of the oil by 10 degrees Celsius in 10 seconds. The specific heat capacity of the oil is dash. Option A, 0.06 joule per gram per degree Celsius. B, 0.18 joules per gram per degree Celsius. C, 1.60 joules per gram per degree Celsius. D, 1.80 joules per gram per degree Celsius. First, we take the data from the question. We are given the electric current I, 3 ampere. We are given the resistance as 20 ohms. We are also given the change in temperature, theta, as 10 degrees Celsius. The time interval is also given as 10 seconds. And of course, the mass of the oil is given as 1,000 grams. We are asked to find the specific heat capacity, C, equation sign. We are using electric current to supply heat energy to oil. So this is electrical method. And when we check the data provided, we can see current I, resistance, and time. So we make use of the fact that electrical energy that is supplied is equal to heat energy gained. So the electrical energy is I squared RT. That's the one that has the letters with the informations above. And the heat energy gained is mc theta. So when we fix the values, we have 3 squared times 20 times 10 is equal to 1,000 times C times 10. So we have 9 times this will give me 1800, will give me 10,000 times specific heat capacity. So the specific heat capacity becomes 1800 divided by 10,000, which is 0.18 joule per gram per degree Celsius. By this solution, option B is correct. Example 2. When equal weights of iron and water are subjected to an equal supply of heat, it is found that the piece of iron becomes much hotter than the water after a short time because dash. A. Iron is in solid form. B. Water is in liquid form. C. Specific heat capacity of iron is higher than that of water. D. Specific heat capacity of water is higher than that of iron. To answer the question, we have to review what we've studied about specific heat capacity and heat capacity of substances. It is only 3 things that determine how hot or cold a substance becomes. And the 3 factors are the mass of the substance, the specific heat capacity, and the change in temperature. Answer. Factors that determine the hotness of a body is mass of the body, specific heat capacity of the body, change in temperature of the body. In the question under review, we are told that both the iron and water, they are of equal mass. We are also told that they are subjected to the same amount of heat energy, which means the change in temperature in both bodies is expected to be the same. So the only reason why the iron and the water, the only thing that will affect their heat gain is the specific heat capacity. Now let's go back to the options. A said iron is in solid form. That's not the reason why it's hotter than the water. Water is in liquid form. That is not the reason. So I'm trying to say option A is wrong. Option B is wrong. Let's look at the specific heat capacity. Generally, specific heat capacity of solids is by far lower than that of liquids. Thus, a little amount of heat energy raises the temperature of solids than that of liquids. So let's consider C. Heat capacity, specific heat capacity of iron is higher than that of water. This is wrong. The specific heat capacity of iron is lower than that of water. C is wrong. D, specific heat capacity of water is higher than that of iron. This is correct, and that is the reason why the iron gets heated much more than the water. D is correct. Right. Option D is correct. Example 3. When two objects P and Q are supplied with the same quantity of heat, the temperature change of P is observed to be twice that of Q. The mass of P is half that of Q. The ratio of the specific heat capacity of P to Q is dash. A, 1:4. B, 4:1. C, 1:1. D, 2:1. Solution. We are told that equal amount of heat was supplied to both objects. So the heat gained by P is exactly equal to heat gained by Q. Heat gained by P equal to heat gained by Q. And to calculate heat gain, we get MC theta for P, MC theta for Q. So that means MP times Cp times change in temperature of P must be equal to mass of Q times specific heat capacity of Q times change in temperature of Q. Let's relate this to the other informations from the question. We are told that the temperature change of P is twice that of Q. That is, theta P is 2 times theta Q. Again, we are also told that the mass of P is half that of Q. Mass of P is equal to mass of Q over 2. If we fix these into the equation, we have mass of P. That means any place we see theta P, we put 2 times theta Q. Any place we see MP, we can as well put MQ divided by 2. If we follow that, I can replace this with MQ over 2 times CP times theta P. I want to replace it with 2 times theta Q. Then I'll leave this side as it is. MQ times CQ times theta Q, and see what you are going to get. 2, we cancel 2 here. MQ, we remove MQ here. Theta Q, we remove theta Q at the other side. We are left with CP is equal to CQ. Therefore, the ratio of CP being the specific heat capacity of P, to the specific heat capacity of Q is 1:1, since they are equal. By this, it means that option C is correct. Option C is correct.